Okay, so we're going to be talking a little bit about the results of assignment 4 and assignment 5, which is coming up. Assignment 4, you probably got, so I guess you got assignment 4 back. No? How many of you got assignment 4 back? Only a couple, 4, 5, 6. Okay. Maybe it was late last night and you haven't checked yet. Anyway. I haven't seen those yet, so it's possible, I'm not saying it's likely, but it's possible that I might look at the scoring and say, oh, let's be a little kinder than that. But I'm not sure. I haven't seen the actual scores yet. Any questions about it? Yeah, go ahead.
So you already know the answer, but why is there a container capacity?
If we're doing a linked list, why is there a container capacity? Oh, if we're doing a linked list, why does the container have a capacity? It shouldn't have a capacity. If it does, it's left over from a previous version of the implementation that was an array. Did you get that from looking from my website? I mean from. Well, so I'm not saying that it's not there, but where did the container capacity idea come from? Was that from the book?
I got my grade back and I failed the capacity.
Failed the container capacity. Yeah, so that you're right. That shouldn't be a problem. So I will look into that. So basically, what it was is what happened is that there's actually a client program online that the author provides, and it's actually on the website that you guys have access to. So if you go hunt around on there, you should be able to find it. We just used that client program that was provided exactly the way it was. Apparently we should have looked more closely and taken out that part where it tested for capacity. But I ran it against mine, and I'm a little confused because I ran it against my solution and I didn't get that error message. So I'll have to look into that and figure it out. Yeah. Any other questions about? Go ahead.
Do you guys use the program that was in the book? You're given the URL address down this test program?
Yeah, I think. Well, I know that. I'm not sure if it's the same one you're thinking of or not. In chapter 6 or in chapter 3, there's a URL.
I saw my friends and I searched for it on the
Oh, okay.
It's available on the website.
Okay. Was it the big long one with lots of tests? Like it had test 1, test 2, test 3.
They had like a switch. They used like a switch to test a bunch of different things and then give you a menu.
Oh no, that one actually that one that you're talking about with the menu actually came straight from the textbook. It's actually listed in here, I think. The one I'm talking about is a different one. I do think that I haven't looked closely enough, so it could turn out to be maybe there's an error with the client that we use. I don't know. Although my solution did pass, but if that's not the case, then I think this is a pretty good exercise in testing your stuff exhaustively, right? Assuming that we end up getting it figured out. But so a lot of you apparently tested your class, everything looked fine, but then when we tested it, things broke. So it'll be interesting for you to kind of take a look at that and figure out what broke and why. And then, so maybe, you know, what you need to test more carefully for next time. I will provide that client program for you. Either I'll figure out exactly where it is online and send you a link or something like that. So you can actually run the test yourself, and you can go in and debug if you want to, or you can figure out more exactly, perhaps, what it was exactly that went wrong. But that is that's optional. I'm not like giving you credit for that, but you should probably do that just to make sure you get what's going on. And then, so I'm going to provide my solution for you to use on assignment 5 when we convert into a templated class with iterators. Okay. So, you know, it's also, I think in assignment 1 and 2, I gave you a client program, which was fine, but I definitely need to give you some situations where you don't get a client program. You have to figure out how to test it on your own, right? That's an important part of this process too. So, all right. So at least if it came back with some errors on it, you know that you're in good company, right? Because there were only 4 that came back without some sort of error on them. Okay. And again, I haven't looked closely at them yet, so you know, for example, the capacity question, maybe there's a problem there, and I need to go back and take a second look. But any other questions about assignment 4? Okay. I want to take a look at assignment 5, and I want to take as long as we need to today for you to understand what exactly it is that needs to happen. Okay. So please don't hesitate to ask some questions to let me know that something's not clear. So just 11? Oh no, you get to it from Kate. Jeez. Got to be a quicker way. I just need to memorize the URL. What? Okay, so assignment 5. How many of you have looked at this already?
I tried to, it wasn't posted yet.
Right, okay. Okay, so basically you're going to turn the sequence class from assignment 4 into a templated class with external iterators. So first, I guess, what's an external iterator? And what's an internal iterator? Someone want to give a shot at that? No? Go ahead, Tom.
Well, it says there that we're going to want to get rid of our smart function, so would that be an example of like an internal iterator system?
Right. So it says here that we're going to be getting rid of start and advance and current. And yes, that's an example of an internal iterator, right? We don't actually see, before the client programmer, we don't actually see any iterator, right? We just have functions that can start it and advance it. An external iterator is a case where I can actually declare a variable to be of type iterator, and then I can set that iterator equal to the first item in the container, and I can advance it. I can actually advance the iterator itself through the container. Okay, so that's what we're going to be doing, and that's the way the containers work in the standard template library. So there's two things happening here. One is you're going to get a chance to sort of see how that works when you're using the standard template library. Secondly, you're going to go under the hood and you're going to create one yourself so that you get an idea of what is under the hood when you're using the STL. Okay? So I might actually skip right to the bottom here for a second before we go on any further, because I provided a client program. This is not an exhaustive client program. It's just something I threw together real quick, and I didn't even, you know, I probably should have written a print function, but instead I just copied the for loop over and over again. Okay, but this should just, if nothing else, give you an idea of how things are supposed to work when you're using an external iterator. Can someone hit the light switch so that the front lights are off, please? Thanks. So here at the top, and stop me if any of this is just fuzzy, right? I think this should be, I think it's pretty straightforward. It's kind of a weird concept, but it's pretty nice and easy to use, I think, once you get it. So if it's fuzzy, let me know it so that we can get it unfuzzied. So I'm declaring a sequence, nothing new there. Just realized, speaking of under the hood, in my actual HTML document, there's brackets string right there. But when a browser interprets the angle bracket, it disappears. So I need to go back and fix that. So just imagine that after every word sequence, there's an angle bracket string after it. Does that make sense? Okay. So here's, I'm declaring a sequence of strings. And then here, sequence, brackets, string, colon, colon, iterator. Okay, so that iterator, you can tell by the context here, where is the identifier iterator defined? It's defined inside the sequence class, right? So in my sequence class, I'm going to define something called an iterator. What is an iterator? Is it an object or what? It's it is a class, but I can tell it from the context. I can't tell it's a class. From the context, I can tell it's a type, right? Does that make sense? Because I'm declaring a variable here, and I'm saying the type of this variable is going to be sequence string colon colon iterator. So in our sequence class, we're going to have we're going to define a new type called iterator. Okay? And if you remember back to the lecture on iterators, if you can remember that far back, you'll remember that we did that, right? We created a class called iterator that we put inside. Okay, so when you first declare an iterator, it's equal to end. Does that make sense? So that probably doesn't make sense. So when you're thinking about iterators, you can kind of think of think of it in terms of, so really what's happening here behind the scenes is that we're setting, when we declare an iterator, we set the pointer that is implementing the iterator equal to null. Okay? And null, so if the iterator is just declared, it's going to be equal to end, because end is a member function that returns, if returns true, no, that it returns a value that represents that the iterator has gone off the end of the list. So let's come back to that. It'll make sense. It'll make more sense in a minute. Actually, let's start here with the printing. Let's look at this for loop, okay? Because I actually think, I know this is weird because I'm not doing things in order of how the code appears, but I think this is going to be make things more obvious if we start here, okay? So if you look right there, what we're doing is we're saying I gets s1.begin. So that's sort of like in our assignment 4, that's saying s1.start, right? It's saying make the iterator I point, I'm going to use the terminology point to, even though they're not technically pointers, okay? Make the iterator I point to the beginning, the first element in the container, okay? And then I'm saying as long as I is not equal to s1.end, which is another way of saying as long as I has not gone off the end of the list. Okay, so end does not, the function end does not return the last item in the list, it returns one past the last item in the list. Okay? Which should make sense to you why it does that, because that's how most things work in C++, right? When we traverse a linked list, if we have a while loop to go through a linked list, what do we say? We say while cur pointer not equal to null. Because when cur pointer equals null, that means it went off the end of the list. Okay? So in that sense, you can sort of think of the end function as being analogous to null. Okay? Yes?
Does it actually return null, or does it return something more complicated?
Well, something more complicated because it returns an iterator, and an iterator can't be equal to null. That doesn't have any meaning, right? By analogy, you can think of it sort of as the same thing as null, but an iterator doesn't actually have a value null. Okay? Under the hood, where it's implemented, that's what it's going to be, yeah. If it's implemented as a linked list. If we're doing a container that's implemented with an array, then s1.end is going to return the index of one past the last item in the array. Okay? So it's very interesting here when you're working with STL, basically you get the best of both worlds between arrays and pointers. Right? You get basically what we're doing here is we're putting a layer on top of linked lists or arrays so that you can't really tell which one you're using, and you get all of sort of the benefits of both. So anyway, sometimes the code is going to look like the analogy is to linked lists, and sometimes the code looks like the analogy is to an array. Anyway, so begin and then I++. So we're going to when we define our iterator class, we overload the plus operator to mean advance. Right? So it's just going to make it point to the next item in the list. Okay? If it's a linked list, that probably means something like current gets current arrow next. If it's an array, it probably means index plus plus. Whatever we need to do in our particular implementation to advance to the next thing in the list, in the container. Okay? So there's begin and end and plus plus. And then the other thing that we're doing in here is the star I. So that just means return the item that that iterator is pointing at. Okay? So I guess when I say sometimes it looks like we're dealing with a linked list, and sometimes it looks like we're dealing with an array, I guess most of this looks like a linked list. The one part that looks more like we're using an array is the I++ part, right? That's sort of how we would do things if it was an array. Any questions about begin and end in plus plus? Okay, so hopefully now that we've looked at that before, my idea was that now you'll have a better idea of what end means. Okay, and when we declare an iterator to start with, that's where it starts by default. That's the default value of an iterator. Okay, now I'm going to call the attach function. The way that I'm going to define the attach function, so basically the only two member functions you're going to write that modify the container, modify the sequence, are going to be attach and remove current. Okay, same thing as the old sequence, except we're going to get rid of the insert function. The reason for that is that I am going to be defining these functions in ways that are a little bit strange because I'm trying to keep things as simple as possible. Okay, so the attach function is going to attach, in the general case, is that it's going to attach an item that's one past the current item, or one past whatever I is pointing at, whatever the argument that we send it. So one difference between our old attach and our new attach is that our old attach function only took one argument. It just took whatever the data was that we wanted to attach into the container. Now we're going to send it two arguments. We're going to send it the data, and we're also going to send it an iterator which tells it where we want to put the data. Okay? It's exactly the way that some of the containers, like the list container in the STL works. Two parameters. So the general case is just what you'd expect, right? If I is pointing to an item in the list, the new item is going to be placed just past that item. And this is a little different from how we did it in the assignment, but this is how it is in the STL. The iterator is still going to point to the same thing it was pointing to before this was called. That makes sense? I don't think I put that in the assignment. Let me write myself a note. Thank you. All right, so that's what it, go ahead.
Just to clarify, so will you be changing attached to the assignment for you'll be posting, or will you have already changed it?
You'll be changing it. So what I'm posting is just simply a solution to assignment 4, and you're going to need to change it. The actual code inside the attach function and the remove current function is a lot simpler than it was in assignment 4. And we'll go over it here in a minute. But okay, so that's the general case for attach. The only question is, what does attach do if there is no current item? Or another way of saying that is if the iterator is equal to end. Okay, and what it's going to do is it's just going to insert at the beginning of the list, at the front of the list. Okay? And the reason I decided that is because that was the easiest thing to do. In assignment 4, if we called attach and there was no current item, it attached it to the end of the list, right? But I'm not going to keep a tail pointer here, just to keep things simple. And so we're going to attach at the front of the list if there's no current item. Okay? So I've actually explained that in the code up above. So maybe I'm doing things in the wrong order here. I'm not sure, but so then I set I equal to s1.begin. So now I is pointing at the first item in the container, and then I see out the first item in the container, just to make sure that it's the. Okay, and so then I'm going to set it back equal to end again. Okay, so this may look a little odd, but this is a call to the constructor of the iterator class. Okay, so the right side of that assignment operator there is creating an iterator that is equal to end, and then assigning it to I. Okay, so I'm calling my assignment operator here, as well as my default constructor. Okay, so basically that's just a way of making it equal to end again. And then I'm calling attach again, so where should quick go? Should be putting it at the beginning of the list, right? So now it should say quick the. The reason I did that is because I wanted to test inserting into an empty list, and then I wanted to test, sorry, I'm using the word insert. I want to test attaching into an empty list, and I wanted to test attaching at the front of a non-empty list. So that's why I set it back to end and tried it again. Okay? And then now I'm going to set it back to begin and see out the first item, and then I'm going to advance the iterator and then see out the second item. And then now the iterator is pointing to the second item in the list, right, in the container. And so when I call attach now, it should put it on at after that, which means it's going to be the third item in the container. So now when I print it, it should say quick the red. Okay. And then I think basically that's everything that's going on here. Well, except, so here I'm just creating an S3 so that I can test my assignment operator. I haven't tested the copy constructor in here, but I could easily do that by just taking this line out and putting the S1 up here on this line instead. And then I'd be testing my copy constructor instead of my assignment operator. With me? Okay. Okay. Now I'm going back to S1 and I'm saying remove current. Okay, so remove current, I really had to sort of do some contortions in order to make it simple. Okay? So what we're going to do with remove current is if there's only one item in the list, it's going to remove that item. Otherwise, if there's more than one item in the list, it's going to remove not the item that I is pointing at, but the item after that. That makes sense? So if my container is quick the red, and I is pointing at the, and I call remove current, it's going to remove red, because red is the next item after the. Yes?
When it's I is equal to N, which it is in that line, right?
So that's going to be a precondition. I can't be equal to N, unless there's only one item. Okay, so that's a little bit tricky. In your code, you're going to basically, you're going to assert that there's at least one item in the list. Then you're going to check to see if there's only one item in the list. If there's only one item in the list, you're going to remove it. If there's more than one item in the list, then you're going to have another assert statement that asserts that there's at least two items. That there exists an item that's one past the item that I is pointing at. Okay? So hopefully I didn't make things more, well, I'm pretty sure I didn't, because it would have been a lot more complicated if I had defined this differently. Because if you try, the only way that you could make it so that you delete the item before I, you'd have to either make the whole thing a doubly linked list so you could go backwards, or you'd have to have a while loop that started a previous pointer and a current pointer at the beginning and traverse the whole linked list until you got down to I. So that would be very complicated. This way the code is very simple. Just that the concept is a little bit convoluted. I mean the specification, yeah.
Is it I equal to in that table right there?
This highlighted?
Yes.
Before I call this, I was equal to end. That's right. Because I had just gotten through this for loop, and when I exit the for loop, I was equal to end. So this is going to remove the first item. Wait. If I call remove, okay. So if I call remove, you know what? Let me get back to that because I have it specified. I might have said it slightly wrong just a minute ago. So let me finish this, and then we'll go back and actually read the specification. So all of this other stuff is just printing and removing current again. The only other thing that I wanted to show you is that I also had to test it for what if I create a constant sequence. Okay, kind of a strange concept. Probably a fairly rare occurrence, but we got to make sure that our class is going to handle that correctly if some client programmer decides they want to do that. Okay, so if the sequence is const, then it's not going to work to use a regular iterator to traverse the array, to iterate through the array. It's not going to work because C++ is not going to let you do that because there's nothing preventing you from modifying the sequence if you've got a regular iterator, if you're using a regular iterator. Okay, so we also have to define this thing called a const iterator, const underscore iterator. That's just another identifier that I made up, right? There's nothing magical about it. I just made up another identifier called const underscore iterator for my client programmers to use when they need an iterator that is a constant. They can't change the sequence. Okay, so if I were to take this off and just put the word iterator instead, I would get an error message saying, a syntax error saying that that I can't do that. I'm trying to think about where it would first come in. I think it would be, I'm not sure. Anyway, can't do it. Now, I just got through saying that const iterator is simply an identifier that I made up, which is, well, you can think of it that way. However, it's not just something I made up. It also happens to be the convention in the STL. So most of the containers in the STL are going to provide something called a const underscore iterator that you can use when you're using their classes. Okay? Okay. All right, let's go through this now and see if it makes a little more sense. So I strongly suggest that you start with the sequence class solution that I will be posting tonight. So I need to do two things before you can start on this. I need to post the solution to assignment 4, and I need to post the code from that lecture I did on iterators, because you're basically going to just copy that code directly. Okay. To do the iterators, you can copy the iterator and const iterator classes exactly as they are from the lecture example that we did when we discussed iterators. The only difference is you'll need to add a member function in each class. Okay, in each class, meaning in the iterator class and in the const iterator class. You'll need to add a member function named link. It doesn't have to be named link. That returns the pointer that that is implementing the iterator. Does that make sense? So the iterator, when it's implemented, is actually a pointer. Okay, in this particular case, the way we're implementing an iterator is it's going to be a class, and the only data member is going to be a pointer at a node. Okay. When you're writing your attach member function and your remove current member function, you're going to need some way of referring to that pointer itself, rather than treating it as just an iterator. And so that's why, but it's a private data member. So that's the only reason I'm providing this function here called link is it's an accessor to get to that pointer. Okay, and I'll actually show you an example of using that here in a minute. Okay, so when I did this, I just copied my code from that lecture that was nested inside the class. Okay, so what I copied was an iterator class, a const iterator class, and 4 member functions. I think 2 begins and 2 ends. Okay, you'll see that when I post the lecture notes. Okay, so I gave you the definitions of the 2 link member functions. Okay, so basically everything you need to do to actually write the iterators is done for you. Okay, hopefully in addition to just copying and pasting, you can take a minute and actually look at it and see if it makes sense. Okay, it's actually not all that complicated. Okay, then the order in which you do things in the class declaration becomes a little bit tricky because there's different things inside there that depend on different things. And so I gave you the order you should do it in. Basically what I did is I had a public section where I defined size type because there were member functions in both of these 2 sections down here that used size type. Okay, and I didn't plan that in advance. I had to execute my program and get a syntax error and go, oh, right, I need to move size type up higher in the class declaration. And then I have a private section where I just have exactly what you have in assignment 4, so the node struct, some pointer data members, and in my assignment 4 I happen to have 2 private helper member functions. You may not have. Okay. Notice that it's 2 data members instead of 4 because I don't have, actually instead of 5, right? If the implementation given in the text for assignment 4, there were 5 data members. The thing he calls many nodes or something, which I don't get that name, so I call it num items. Head pointer, tail pointer, cursor, and precursor. Okay, you don't need cursor, precursor, or tail pointer. So all you're going to have is num items and head pointer. Okay, so a lot of the work here actually consists of going through your code and taking out references to cursor and precursor and tail pointer because you don't need them anymore. Okay, and then finally at the bottom there's a public section where you've got the stuff that you copy from the assignment, from the lecture, which is 2 classes and 4 functions, and then your standard normal public member functions. Okay, it turns out there's going to be 9 of them. There's going to be the big 4, there's going to be size, and then there's going to be 2 versions of attach and 2 versions of remove current. Have to have 2 versions of each because there's going to be a const version and a regular version. Yes.
How do you get remove current for a class version?
Because even though the remove current doesn't modify any data in the container, it could. And so C++ won't let you call it if the sequence let me think about that. So if the sequence is const, you wouldn't want to be calling remove current anyway. So I might have to think about that. Yes.
The same would be true for attach, right?
Yeah, same thing. My brain's not quite getting around that right now, so I'll have to think about that. What I do know is that my program wouldn't compile when I didn't have them. So I'm pretty sure you're going to need them. Let's look at that code again just for a second. Yeah, I never called attach, or in this code I never called attach or remove current on S4. I'll have to think about that. Adding to my list here. Okay. Okay, so because we're using external iterators now, the specification of the class will have to change quite a bit. I think I'm repeating myself here, huh? Up here I say you'll want to get rid of those functions while you're at it. That's because that's what I had originally and I added to it. But down here I say it again. You can simply delete start is item current advanced and insert. You can also delete the data member's cursor, precursor, and tail pointer. In order to have a fully functional sequence, we would need to use a doubly linked list. That's what the list class in the STL uses. Okay. So to keep things simple, I'm going to use the following two member functions to modify the sequence. I think I've talked about this already. Attach takes two parameters, an item to attach and an iterator. Attaches the item as the next node in the list after the node that the iterator is pointing to. If the iterator is equal to end, the item is inserted at the front of the list. Okay? Very short function, 9 lines of code. When I did it anyway, got an assert, got a couple lines to set things up, and then an if-else statement with 2 statements inside each branch. That's it. Okay, so the 2 cases are, if the iterator is equal to end, do one thing, and then otherwise do the general case. That's it. Sorry, I'm just thinking again about the question about whether we need const versions of attach and remove current. Okay, so here is where I talk about the precondition for remove current is that size is greater than 0, and okay, so this part you can assert right at the start of your remove current function, but this part you're only going to want to check if the iterator is not equal to end. Okay? So if the iterator is not equal to end, then not only does the iterator point to an existing item, but there's at least one more item in the list after that item. Okay, so that's the precondition for this function. And then the item after the item that the iterator is pointing to is the one that will be removed from the list. Just like attach, there's two cases. You'll want to assert size greater than 0 first. Then if the iterator is equal to end, do one thing, which is remove sorry, I didn't actually say this anywhere. Is there any place in here where it tells you what to do if the iterator is equal to end? I don't think so. So if the iterator is equal to end, we're removing the first item in the list. And then otherwise do the general case, which is remove the item after the item that the iterator is pointing at. In both attach, okay, so I'm moving on. Any questions about the specification of attach and remove current?
So remove current, the assertions will fail if size is equal to 0, or if the iterator points to the last item in the list?
Correct. That's a good way of saying it. So the assertions will fail if size is less than 1, or if the iterator is pointing at the last item in the list. Well, it's not quite right, because if size is equal to 1, we have to put the value, the iterator value. Right. That is right. So if the iterator, what I was thinking about is if there's one item in the list and the iterator is pointing at that item, I was thinking that was going to be okay, but that's not okay. Okay, so let me try saying that again, because I think you had it right. The assertion should be, we're going to, instead of saying it negatively, let's try saying it positively. My computer just dinged, but I'm not sure why. Hold on. Huh. No one has a hand up or anything? Did I just imagine the ding? Okay, let me try that again. So let's say the assertion positively. Either size is greater than 0, no, it has to be both, right? Size is greater than 0, and, wow, I don't know why this is so hard for me to get my brain around. Size is greater than 0, and size does not point at the last item in the list. I'm sorry, the iterator does not point at the last item in the list. Size is greater than 0, and the iterator does not point at the last item in the list. Yes?
I thought you said that if it's pointing to the last item, you'd be confused with the first item.
Close. That's what, and in fact, that's the same confusion I was having. It's not if the iterator points to the last item in the list. It's if the iterator is equal to end, which means that it's pointing one past the last item in the list. Okay? So, I think this is sounding more complicated than it actually is when you sit down and start to think about it. Okay? I hope anyway. So, just to state that one more time, the assertion is two things have to be true. Size has to be greater than 0, and the iterator cannot be pointing at the last item in the list. It can be equal to end, or it can be pointing at any other item in the container. I keep calling it a list. But it can't be pointing at the last item in the container. Does that make sense? Why it can't be pointing at the last item in the container? Someone tell me why it can't be pointing at the last item in the container.
It's going to try to modify the next one.
It's going to try to remove the item after the one the iterator is pointing at, and there's not going to be anything there to remove. Okay? So let's talk. Let me just try to see if I can state again what the remove current function does. Okay? If the iterator is equal to end, it removes the first item in the list in the container. Otherwise, it removes the item after the item the iterator is pointing at. I guess I could just say after the current item, and that would be an easier, simpler way to say it. Yes?
If there's only one thing in the container, then wouldn't the iterator be pointing at that thing, and wouldn't it be the last thing in the container?
If there's only one item in the container, so the question is, if there's only one item in the container, wouldn't the iterator be pointing at that item because it's the only item in the container? And the answer is not necessarily, because the iterator could also be equal to end.
Right, but if it is equal to end, and if it is pointing to that item, then what is it going to direct it to?
That's not going to meet the precondition.
Okay.
So we don't have to worry about that case. So if there's one item in the list and the iterator is pointing at that one item, then that fails to meet our precondition. Because part of our precondition said that there has to be an item after the one that I was pointing at. To put that in, so I'm saying it that way, but that's actually just a complicated way of saying it can't be pointing at the last item in the list. It's a better way to say it. Okay. Any other questions about remove current? Okay. I'm going to work on this wording here and make it more clear. Okay. The link function. In both attach and remove current, you'll need to use the link function. And here's a sample statement taken directly from the solution to give you an idea of how it might be used. I is the iterator parameter. Okay, so I can say I.link arrow next. Okay, so that just tells me the node that the iterator is pointing at, arrow next, okay, gets that same node, arrow next, which basically means make the next pointer in the current item point at 2 items down instead of pointing at the next item. Want me to draw a picture? Let me draw a picture real quick. So, here's our list, and we actually don't really care what comes before this in the list or what comes after this in the list. for this quick example that I'm doing. Okay, and up here is okay. Technically, what this is that I'm drawing a picture of is I dot what I called my pointer data member was current. Okay, or which is another way of saying I dot link. Okay, so if you look inside my class declaration, the private data member in the iterator class is called current, and it's a pointer. And so we're going to say that this is pointing right here. Actually, no, let's make it so it's pointing here. Okay, and so this statement over here, the I.link arrow next gets I.link arrow next means I.link is this whole thing here. Actually, I.link is this pointer. I.link arrow next is this cell right here, which is pointing over here. And we're saying make that, instead of where it points now, make this point to list arrow next, point to the same thing that list arrow next is pointing at, right? So that's this arrow. So what we're saying there is disconnect that and make it point here. Okay? So that's basically the meat of your remove current function right there. Yes?
Then how do you delete that?
Well, hopefully, remember this is taken completely out of context. So hopefully you're going to have some other way of getting to that node already set up so that you can then just delete it through that other way that you have set up. Okay? And now, you know, when you're doing this, probably what I would do if I were you is I would not worry about the memory management at first, and not worry about memory leaks and deleting the old things at first, just so you get something working. And then you can go back and you can fix up the memory. This is called memory management, right? You can go back and fix up and make sure you have the delete statements you need in there. Okay, that's just another example of iterative, incremental development. Okay, where you just get a little bit working and then you start adding stuff in, so that it's easier to identify what caused your error, right? I just realized we've been going for a really long time. Almost done with this. The changes to the big four will mostly be a matter of removing unnecessary code, such as code that relates to cursor or precursor or tail pointer. The delete sequence function, so you'll see in my solution that I give you, I wrote a function called delete sequence, which wipes out the whole sequence, so I can call that from both my destructor and my assignment operator. And that doesn't change at all. Size doesn't change at all. And then here's the client program. Okay? So I think that I've given you quite a lot of what's going to have to happen here. The changes you're going to make are pretty minor, not necessarily saying that they're easy or simple, but they are small, other than the fact that you're going to be getting rid of big chunks of code. You know, you're going to delete your whole insert function and advance and all of those. Any questions about assignment 5? I think I have it due next Monday, right? So my November 12th. So I'm hoping that this is a 1-week assignment. If I turn out to be wrong about that again, we'll make some adjustments that we need. But don't count on that, because just because you're having trouble with it doesn't necessarily mean everyone else is. Question? Yeah?
So assignment 6, you want to help this one?
Yeah, okay, so assignment 6, there's not actually going to be anything for you to turn in. So I'm still sort of carving out a placeholder for it so that I'll have a lesson 6, and it will have like links to some of the code that I do in class or something like that. Okay, but there's not going to actually, you're not going to actually do an assignment, a programming assignment. Okay, same with assignment 10. Okay, so if everything goes according to plan, there's going to be an assignment 7, 8, 9, and we're done. And we have 6 weeks left, including this week, and then our final. So actually our final is 6 weeks from today, I think. Is that right? Yeah. Okay. So hopefully we'll be able to squeeze 3 more assignments in there. November 12th. So I gave you 1 week for assignment 5, 2 weeks for assignment 7, 2 weeks for assignment 8, and 1 week for assignment 9. So that's 6 more weeks. That also makes it so that the last assignment is due the day of the final. So, for better or for worse, I could just make it due the Friday before if you prefer that, but I'm guessing that's probably not your preference. Hey, any questions about assignment 5 or about our schedule? Okay. Let's take a break and come back. We'll only have 20 minutes when we come back, but that's okay. I think we need a break anyway. So we'll come back at 10 o'clock. Okay, so we're going to continue talking about stacks now. And I think I just have one more quick thing that I want to run by you that's sort of tangentially related to stacks before we move on. And that is, I want you to understand infix notation and prefix notation and postfix notation of expressions. Okay? If you have no idea what I'm talking about, that's why we're here. So infix, prefix, postfix. And this may seem a little bit weird because it might be hard to understand exactly why we even care about this at this point. So this is one of those kind of things that's going to be abstract for a while, and you just need to think of it as like, a fun puzzle or something for now until we get a chance to do some more significant stuff with it. But so basically the idea is, let's take an expression like 2 plus 3. Okay, that's called infix notation because the operator is inside, in between the two operands. Okay, if we want to convert this to prefix notation, we're going to say plus 2, 3. Okay, so in this case, the operator comes before the operand. So the way you would do this is the first thing you see is the plus sign. So now you just remember, okay, the next two numbers that I process are going to be, I'm going to apply this plus operator to them. Okay, and then you read the 2 and you say, okay, that's one number, but I still need another one. So then you read the 3 and you say, okay, now I have 2 numbers. Now I'm going to evaluate them by applying that symbol that I was saving from before to those 2 numbers. That's how you would process that. So the way that that is related tangentially to stacks is that you would probably use a stack to implement evaluating this expression. Every time you see an operator in prefix notation, every time you see an operator, push it on the stack. Every time you see a number, look at what's at the top of the stack. If the thing at the top of the stack is an operator, then you just push the number. If the thing at the top of the stack is a number, then you pop off that number and pop off the operator underneath that and apply that operator to the 2 numbers and then push that result back on the stack. That's the whole algorithm right there. So it's not really important necessarily. Let me be clear here. I explained that so that you would have at least sort of a vague idea of the connection between what we're talking about and stacks. You don't need to be able to reproduce what I just explained. Okay, but you do need to be able to convert back and forth between infix and prefix and postfix. That's what you need to do. That's what you need to be able to do. So postfix notation is actually even easier for us to process, and that's going to be 2, 3 plus, right? So for postfix notation, it's very easy for a computer to write an algorithm to process them, because you just see a number, put it on the stack, see a number, put it on the stack. Every time you see a number, you put it on the stack. Every time you see an operator, you just pop the last 2 numbers off the stack, apply that operator to those 2 numbers, and push the result back on the stack. That's all there is to it. Okay? So let's just see if we can work on some slightly more complicated examples. Let's do there's infix notation. Okay, so postfix notation is going to be, what do we do first? Addition. We do the addition first. So we're going to go 2, 3 plus. And then the next thing we do is the multiplication times 7. So we're going to do 7 times. Okay? Prefix notation. Interestingly, we start when we're converting into prefix notation. The first thing we push on the first thing we want is the last operation that gets done. Okay.
So we want the 7 multiplication symbol there.
So we're just talking about operators here. The first thing that goes on the stack is going to be an operator. Which is the last operator that's going to get done? A multiply. Okay. And if you understand what I'm talking about with the stacks, that should make sense, right? Because the first operator we see is going to get put on the stack, which means it's going to be the last one out of the stack. So last thing we do is times and then what's the next thing we do? Plus.
Would it be 73?
And then, well, we're applying the plus to the 2 and the 3, right? So we got to put the 2 and the 3 next. And then we put a 7. Whoop. 7. Okay? So if you were trying to process this, you look at the star, ignore it for now, put it on the stack, however you want to explain that. And the plus, put it on the stack. You read a 2 and a 3, you go get the plus so that you add 2 and 3. So that's 5, and the 5 goes back on the stack. And then the next thing you read is a 7. So you pop 7. So you pop the 5 and the times off the stack, which tells you to do 5 times 7. Okay. And again, postfix is even simpler. Push the 2, push the 3. You get to the plus. That means you're going to pop the 2 and the 3, add them together, and push a 5 on the stack. Then push the 7 on the stack. Then when you hit the multiply operator, you pop the 5 and the 7 off the stack and multiply them. Let me give you something in postfix and see if we can convert it to infix. How are we going to do this? As you're processing this, what's the first thing that's going to happen?
Multiplication.
The multiplication is going to multiply the 5 times the 3. So let me just go ahead and start by putting that in parentheses. Okay. Then what's going to happen next? Going to add 7 to the 15. Okay. So now what I have at this point where the cursor is, that's how much of the expression I have processed so far. Okay. So then if so then what's on the stack is 22, right? 3 times 5 plus 7 is 22. Okay, so then I read the 4 and a minus. That means minus 4. Okay, so you could practice going back and forth. Maybe let me translate that into infix now. The last thing that's going to happen is the minus. And then I'm going to do plus. Now this is kind of an maybe an unfortunate example because everything's done exactly in order here, right? Left to right in the infix example. But which means that we're just going to have all operators here first, and then 3, 5, 7, 4. Okay. So you can see that the times is going to get, the times is going to get applied to the 3 and the 5, and then I'm going to add that result to the 7, and then I'm going to subtract 4 from that result. Okay, so what I probably need to do is give you some exercises just so that you can try this out on your own and make sure that you're able to do it. Try to decide if I want to. Let's do one more. I guess I'll start with infix and convert it to something else. So sorry, I can't read my book because of the glare. Okay. Now this is fully parenthesized, which means that every sub-expression has parentheses around it, whether they're needed or not. Okay? So looking at this, if we're going to translate this into postfix notation, the first thing that's going to happen here is the 3 plus 7, right? So I'm going to say 3, 7 plus, and then the next thing that's going to happen is this division, right? So I'm going to do 8 for divide. And the next thing that's going to happen is I'm going to multiply those two results together. Okay, so that means right now, at this point in my processing, I've got a 10 on the stack, and I've got a 2 on the stack. Okay, so if I say times now, that means I'm going to pop those two things, those two results, and multiply them together and put the result back on the stack. So at this point, I've completely processed up to the minus sign. Okay? What's the next thing that happens? 2 times 6. So I got to say 2, 6 times, and then I put the minus sign in there to subtract those two results. So there's postfix. And let's just do prefix, and then we'll be done. So for prefix, there's two different ways you can look at it, whatever works best for you. What works best for me is I start with the last thing that's going to get, the last operator that's going to be applied. The other way would be to start with the first operator that's going to be applied and start in the middle of your prefix notation expression and work outwards. But let's just do it this way. So the last operator is the minus, so I put that down. And what's going to be minused is the result of that multiplication on the left. So the next, right. 2, 6, 10. The next thing, actually the next to last thing that's going to get done is the 2 times 6. Right? So I'm going to do times 2, 6. And then the next to last thing that's going to happen after that is the multiplication. So I'm going to do the multiplication, I'm going to have to do the plus 3, 7, and the divide 4, 8, 8, 4. Oh, yeah. And then multiply those together. Oh, I switched from prefix into postfix, huh? Eek. Okay, so I times the 2 and the 6 together, and then I'm going to subtract that. Oh, I've already got that subtracted. My brain just suddenly turned off. Why don't we finish this up next time? You know, I guess my brain just turns off at 11:20. You can't do anything else. So we'll finish this up next time.
It's been really friendly. It's letters on it.
Oh, sorry. See, I told you my brain was off.
Yeah, 30 minutes.